And welcome back to the Astro Imaging channel. I'm Alex, and I'm going to be helping out today hosting the program. We are going to be talking about plate solving. And just a second. I have to stop my other feed over there. I would strongly suggest that everybody sign on to the chat group over there. And if you haven't seen that, let me start sharing my screen. And back, if you just pull out the chat screen over here and sign in, you can ask all your questions. Oh boy, there are some questions already. Well, good. Tolga and Eric are gonna read through those, and they're gonna get ready for some stuff. We aren't gonna have an image of the week today. We do have some submissions. We hope you continue to make your submissions. Today we're gonna be talking instead about plate solving. And plate solving is a very interesting thing, as you know. Please put any questions you've got in there. Yes, we will be talking about SGP. We'll be talking about plate solve too, but we'll be talking about all sorts of plate solvers, not just plate solve too. Whatever kinds of questions you've got, put them in over there. Over on the left side of the screen here, you've got a picture of a star field. And on the right side of the screen, you can see that there's also a very large sky field of stars rising over the Devil's Tower. Now, this one on the left is someplace over on the right. And the question, of course, is, for a plate solver is, where can I find this group of stars in this mess of stars over here? And while it may seem hard to do, it's actually quite possible if you've got a good plate solver. This is a plate. It's a very famous plate. It's the plate that made Hubble famous eventually. He found on the 6th of October, 1923, a variable star right there. And since they knew how to measure distances somewhat based on variable stars and how they could measure brightness of the variable star based on the period of its variations, he could figure out that this galaxy, whether he didn't know it was a galaxy, it was just a big nebula at the time, was separate from the Milky Way. It is basically a piece of glass, and it's coated with a gel with photosensitive chemicals on it. And the astronomers preferred using glass because it was very stable. It didn't move around like film, like plastic-sized film is and stuff like that. When you'd hold one of these things up to the end of a telescope, you'd get little dots on it. And these dots, of course, this whole thing's negative. So these dots are stars, and the big dark areas in here are the nebulous areas. They happen to be stars in this case, but sometimes they're gas blobs and things like that. Anyway, back around early 1900s, there were computers. This is a computer right here. This is a computer that is, this is Miss Cannon, and she was famous for studying these glass plates and figuring out for every star here a number of things about them, including their very precise positions. And she also figured out some other things about them, what spectral class they were in, and a few other things. And she put them together in a whole catalog. As time progressed, they got machines that could do this. This is an AGFA scanner that they actually put a plate in, and they checked it out. And as you can see, they can put the plate in and copy where all the stars are and digitize it. When you digitize it, you actually get something that looks like this. In the Henry Draper catalog at the Harvard College, they've got numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and thousands of stars. And for each one, they've got a number of pieces of data on it, including the right ascension and the declination as of 1900. So they've got page after page after page of this, or in modern terms, they've got a database of this, of where all the stars are and all their positions. Now, the next step in finding out where something like this is in a field like this is matching those positions off this table, or the computer version of this table, to where stars are in this. Now, how does one do that? It is rather mystifying to me. And I want you to know that everything I say here is going to be my opinion. There are some people who actually know this stuff, but they aren't here tonight as far as I know. If you do know this stuff, please correct whatever I'm saying, because I don't want any misinformation going out there. I'm just a guy that tried to figure out what plate solving is. And so I looked at a bunch of stuff on the internet and found some answers. And I'm going to tell you what I think I found. May not be 100% right, so don't go quoting it at your next astronomy meeting, but this is in general how plate solving works. Before we get to it though, let's make sure we understand some definitions of terms. There are 5 terms that are somewhat mooshed together here that we need to straighten out which one means which. Plate solving, centering, synchronizing, aligning, and model building.
We should also add blind solving.
And blind solving is coming in here a little bit later. Yeah, we're going to be talking about that because we need to distinguish between solving and blind solving. So thanks, Tolga. Plate solving is comparing this picture, the one I've got right now in my camera, on my computer, in my hand, or on a big glass plate, comparing it to a database of where all the stars are so that I can determine where this particular picture is in the sky. It is not centering. Centering is moving the mount so that a telescope points to a particular position. Now, for some time, we've been using GoTo in our telescope mounts, and they use mechanics and electronics and also a database to move the scope as needed a certain distance to get to a certain place. Well, some last few years, the plate solving has come into its own in helping with this. Plate solving is used to help center, but plate solving is not centering. Plate solving is a tool that centering uses to confirm that something is centered. What it does is, in plate solving, you take a picture, an existing picture, or you go ahead and take a new picture, and you digitize it. I'll show you what I mean by that in a minute. And then you find out where that picture is, and then you say, hey, telescope, move to, this is where you are now, because I just took a picture with it. I want you to move to this new position. Okay, and so it goes off to the new position using whatever it uses. It's mechanics, it's electronics, it's GoTo, however it wants to get there, it gets there. And now it takes a new picture and it plate solves it again, determines where that new picture is. And if it is where it's supposed to be, it says, okay, I'm here. But if it isn't, it goes through and centers again. And it iteratively goes through centering, plate solving to check to see that it's there, and then plate solving and centering. And that whole operation is called centering. Plate solving is only one part of that operation. So when you're saying you can't get plate solving to work, you have to ask yourself, can I not get this picture to determine where it is? Is for some reason my plate solving not able to figure out where this picture is? Or having figured out where the picture is, my mount can't seem to get there. And that's the difference between plate solving and centering. Now, there's some other words that are thrown in at the same time. One is synchronizing. This is telling a mount where it is when it's at a particular position. It's saying, okay, mount, you are now right at right ascension 12, 24, 13, and declination 93, or that would, yeah, your declination, 93 would be hard to do. 40, 17, 16. It says that's where you are right now. The way we used to do it is we used to point to a star that we tell them out to go point to a star, and then we would look through the telescope or look at the picture that the telescope was taking, and we would say, hey, are you, is that star right in the center? I know what the right ascension and declination is for that star, and so did the computer hand paddle, but I've got to make sure that the star is focused right in the center there. Okay, so I move my mount around until it is, and then I synchronize it. I say, now you are on that spot. I can see in my eyeballs that it's pointed right at it. That's what we used to do. What we do nowadays with plate solving is we go and we go to a position that we think is where it's supposed to be. We take a picture and we plate solve that picture, and then whatever the solution is to the plate solve, whatever the location of the plate solve is, we synchronize the mount to that position. Then we go ahead and go to the position we really want it to go to. But synchronizing merely tells the mount that it is at a particular position. Aligning is a little more, it's a series of synchronizings. And these are, I'm using the word alignment. Many of you have heard of 1-star alignment, 2-star alignment, 3-star alignments. Depending on what kind of amount you've got, it might be called something else. But basically, if you just point at 1 star, you'll know that you're aligned for that one position. But as soon as your scope moves, it may be moving someplace completely different from where it's supposed to be. Usually, you align a mount in the first place, particularly a German equatorial mount, by its physical centering. Namely, you put the counterweight down, and it's at 90 degrees, pointed north, and it's polar aligned. Therefore, it knows where north is. That's point number 1. Then you go to someplace, let's go to Betelgeuse, and Betelgeuse is not quite in the center, so you move your scope around until it is, and then you tell it, Betelgeuse is right here. Now you've got 2 alignment points, the initial counterweight down position and Betelgeuse. From that, your mount can already tell certain things. You start adding that 3rd point and that 4th point and that other points, and you start model building. Model building is using alignment to tell the mount electronics many, many parameters about the mount and the sky behavior. This collection of parameters down here, azimuth misalignment from pole, elevation misalignment from pole, after you've used, this is for Gemini, if you get 1 star, then you'll have 2 alignment points, the counterweight down position and Betelgeuse, or whatever star your first alignment star is. Then you go to a 2nd star. With the first one, all you can tell is probably these first 2 elements. But when you go to the 2nd, 3rd, and then you go over to the other side of the mount, you can start telling things like gear play and mirror flop. So when you take 5 or 6 of these alignment points, synchronizing on each one, you start to build a model. Now, if you're really dedicated and you've got the sky with T-point, you can go out and build a 150-point model. And that 150-point model means that you've taken pictures randomly all over the sky, and you can take into account all these things: mirror flop, index or counterweight flexure, axis non-perpendicularity, which this stuff's called cone error. Okay, so you can tell all that stuff once you've built a model. If you've got an absolutely wonderful model, and you are also going to be able to tell the refraction, how refraction is affecting the telescope and things like that. Okay, so there are 5 different concepts here. Let's not confuse them. People often do. They say, oh, I did a 3-star alignment and I still can't, and my plate solving's still not working. And do I have to polar align still? You know, the polar aligning is a whole nother thing. But plate solving is part of centering. Centering is not synchronizing. You synchronize as you're centering. You're also aligning, means you're using several alignment points at the same time. And when you start building with several alignment points, you're doing model building. Tolga, Eric, do we have any questions I should be answering yet, or should we hold off?
Yeah, we don't have any specific questions. There's
Okay.
a chat going on, but I'll let you know if there's a specific question.
Okay. Now, it's always been amazing to me that you can look at something like this and find it over here. I mean, what is the relationship of this star to that star that makes me able to figure out that, hey, that's those 2 stars? Well, I perplexed over that for a while. And this is from Elbrus, and you can look up the URL here. This is a picture of a star field. The first thing Elbrus does is it identifies the stars. And we're going to go through this 2 or 3 times. So it's got to figure out what's the stars. And stars are areas of light that are higher than the background area. So here's the background area, and here are the stars. They come up above, and you have to define this line right here. Once you've defined the line, anything that rises above it, that location is going to be considered a star. Anything below it is not going to be a star. So the first step is to go through and find the stars, the brightest stars in the picture, the ones that you want to identify. So you take a picture and you identify where the stars are. Now you start making diagonals. You connect this star with this star and that star. And in the case of Elbrus, you look for a pattern in this area of the sky where the angle from here to here is X, and the distance from here to here and here to here matches. That's what you do in Elbrus. In other plate solving programs, you do different things. Remember, I told you at the beginning here, I don't know what I'm talking about. What I'm doing is reporting to you what I think I've read. And from what I've read, there are many ways to do this. My sources are a couple of places on the web, a couple of discussions I've had with people, one of whom spent a long time developing a very famous system of plate solving, and we were drinking beer for about 3 hours while he explained to me. I didn't understand it all, but it was a lot of fun at AIC one year, just sitting there listening to him explain, because it was really a mystery to it. So what you do is you find all the relationships between this, and in Elbrus's cases, it guesses what this one should be by checking its database, and then it starts making all of the other triangles. And there is only one triangle in all the, or only one polygon, they call them, in all the heavens that can match this set of angles and these distances. The way it finds it is it looks for distances between 2 and an angle, and then goes after the others. Now, if it had to do that from scratch each time, it would take a heck of a long time, because there's hundreds and hundreds and billions and trillions of stars out there. In fact, almost all the work has been done before. Remember I said that they match it to their database? This is how they pick up their database. Each of these is, say, 1 degree across and 1 degree across. So it's a 1 degree square. So their index is 1 degree. Well, this area here is 1 degree field of view. I'm sorry, not each of these. And what they'll do is they'll grab all of these stars here, and they will find the 10 brightest stars, the 10 things that make stars. Oh, they take a picture. No, they don't take a picture. They use pictures that were already taken, like the Palomar Sky Survey or the Hubble Guide Star Catalog or something like that. And they will map out where all the stars would be and their relationships between them. And then they pick up this whole grid and they move it over 2 spaces so that it now fits over here. And they do the same thing. Then they move it over 2 spaces and they've got, remember when I showed you this way up here? Where did it go? Where'd it go? There, that, okay? They've got all of this stuff in a computer organized according to these fields of view all across the sky. Okay, and they go all the way around and they get all that. And they compute all the angles that they're going to need. And then they put them all of these angles are in a code. And so when they find, let's see, when they find this particular angle and this particular, these 2 particular distances, there's only one place that they, well, there is one place that they can find that. They know to look in this particular area and they find that relationship. When they find that relationship, they figure, okay, now let's see if this other relationship holds too. And then they go through and they check the whole, and if they get more than a certain number to match, they go, okay, we got a match. We know where we are. And then they just compute where the middle of that polygon would be. And that's what it is. Now, there's another way to do it.
Alex.
Yeah.
Alex, there's a small question. It's kind of related. The question, John Adastra asks, is there an optimal exposure time to use for plate solving?
There's not one optimum. Everybody has an optimum one. And when we get to talking, we're already starting to talk about it. When I said they look for stars up here, they have to find a certain number of stars. Okay. And so, yes, you have to have an exposure that generates enough of these stars, but not too many, because if you overexpose, you're gonna get saturation, and you're not gonna be able to tell exactly where things are as well. There is a little bit of a slide about that. Let me tell you about a different method for finding the codes. That last one was polygons. This one has to do with quads of stars. If you find 4 stars, any 4 stars, and you take the 2 most distant from each other, and then you take the other 2, and you build a code for them based on where they are in relationship to each other. And I think I've got a better example of it. Remember this picture? We've seen it many times so far. I want you to note these stars right here. These are 4 stars. These 4 right here. I'm going to run them through a wavelet filter, and you can see that they stand out a whole lot more from the background when I've run them through the filter. So that's what you have to do first. You don't have to do it. That's what the program has to do first. It has to identify, and then it picks its 4 stars that it's going to use. And here is that same pattern. Here's that same picture we just had. Here are the stars. This is an inset of this. This is a duplication of this. I've A is right here, B is right here. Those are the 2 stars that are most distant. Let's call this a simple XY grid, where at the origin, 0.0, that's 1 star. Oops, back up. And then the farthest away star is the B star. That farthest away star is 12 units out and 8 units up. So we're going to give it a location of 12, 8. Then I'm going to go to the 3rd star. Where's the 3rd star? This one down here, I guess. It's 10 units out and 3 units up. And the 4th star is 4 units out and 7 units up. By the way, something could be negative. If this star was down here, that would be perfectly valid. It'd be -7 or something like that. So I've got a code up here. The A is always going to be 0, 0, and then there's 12, 8, 10, 3, 4, 7, and 4, 7. That's that first part right up to here are the locations of my stars. Now, that looks a little weird to us, but it's very recognizable. It's got its own set of numbers. And there aren't a whole lot of other combinations of stars that have that set of numbers. So the rest of this is an RA and a deck. So if you find 4 stars, well, first off, what you do is you go through the entire sky, and with hour after hour after hour of computation, you define all the possible quads, the groups of 4 stars. You define what this relationship is. But once you've defined it, it is only this, a big long list, okay? And all you've got to do is go through the list. I don't know what all the computer terms mean, but there's words like hashing and algorithm and stuff like that that are involved in this. And it's fairly easy to find the only place in the sky where that peculiar set of numbers fit. And that happens to be at 1203. Well, that may not be true because there's a couple of problems with this. First off, there's noise. There's problems. There's maybe poor exposure. There's various other things. So these numbers would actually be kind of estimates of what the numbers would be. Okay, so just to make sure, you go ahead and include this star, this star, this star, and this star in a quad. And you do exactly the same thing. And if you find this match, this original match, and that match, and these 2 stars are somehow coordinated, hey, you're getting pretty close to knowing exactly where you are. And that's kind of how plate solving works. The guy I had the beer with at the AIC, Advanced Imaging Conference, that long time ago, he does triangles, okay? He doesn't do quads, and he doesn't do polygons like these guys do. And they all have slightly different ways of quoting their catalogs and stuff like that. But generally, it's a process of defining beforehand where everything is, and then taking a look at a picture, finding out its dimensions or whatever, and finding out where you can find those dimensions someplace in the celestial world. So this is one group of 4 stars, one quad here. Well, that same quad, when you match it to all the other quads around, if you find 15 quads that all seem to match pretty well, you can be pretty sure that you got it. This is a Google presentation from the guys who do astrometry.net. And that's the one that 90% of you guys are probably using. So if you want to find out how it's working, you can go to this this workshop right here. It's a PDF, and you'll find out all that information. Okay. Now, if you can understand it, please come back and do a show on the Astro Imaging channel and correct all the bad information I've just passed out. Okay. What we know so far is that it's absolutely necessary. Oops, I'm getting lost. Help me, help me. We have to identify what our stars are. We have to know our scale, and we have to know the starting location. I'm going to stop here and ask Toga and Eric if there are any questions. Wake up, guys.
Now I'm just shuffling to find the microphone button on the screen. I had my mouse. No, we don't have any questions right now.
Okay, we got questions, but not necessarily about okay. So 3 things that are going to be essential that if you want your plate solver to work is you're going to have to be able to identify the stars. See, you got to know which are stars and which aren't stars. You're going to want to know the scale. How big are these squares supposed to be when you're looking at it? And you're going to want to know, and there, I don't have a slide for this that we've looked at already, but you know, if you're going to start looking for something, you kind of want to know where to start looking. And that's part of your hint information. Okay, here's that original picture we had from before. And here's how they decided what the stars were. And here's the identification of the stars. You guys remember this picture, the detail of the NGC 7000. If you extract the waves from it, you'll get a picture looking something like this. And frankly, you know, you can pretty well tell where the stars are here, can't you? But look what else you got. See this stuff up here? Is that a star? Is that like one long, huge star? What is that? It gets worse the more nebulosity you got. Here's a super stretched version of this. These are the pictures that were on the last page. Here's a super stretched version of it. And you can see that the more nebulosity you get, oh boy, there's a whole lot of stuff. A lot harder to tell here where the stars are, isn't it? Okay, yeah, sure, there are some stars and everything, but you got a whole lot of other things that could be distractors. So as far as star identification, if you want your Platesolve to work, you want to start with about 20 stars or so. And they should be bright enough stars. They don't have to be real bright. They don't have to be first magnitude or anything like that. Just bright enough so that they distinguish themselves from the background easily enough. They should not be saturated, because saturated stars don't give as good a position indicator there, because you can't tell where their center is as much. If you've got a whole lot of nebulosity in the picture, you might have a tougher time running a Platesolve on it. And watch out for noise. If you've got hot and cold pixels, your Platesolver in running its first filter may decide that some of these things are noise or some hot pixels, and they're trying to place hot pixels in their grid, and that just won't work. So this should answer the question, what is the ideal exposure? With both of my cameras and both of my telescope tubes, I find a 6 to 8 second exposure is generally enough to determine enough stars to, you know, give me a picture that will show my stars like that. Okay, but you'll have to find something. If you take a picture and you look at the picture and you can't see a lot of stars in it, then you probably need to increase the exposure. If you've got a whole lot of stars, you're just confusing the thing. You don't need to, you know, you don't need to waste that much time taking the picture. This is scale, the discussion about scale. Each of those pictures, when your Platesolver starts to look, it wants to look at stars spread over a certain area of sky at a time. So it needs to know the field of view. Field of view, and I'm using Sequence Generator Pro in this particular example, is determined in various places. Under Tools, Equipment Profile Manager, you pick whatever your profile is going to be, in my case, the Outhouse Me 10-inch narrowband. And I go under the, here under Camera, okay? Down here it says Scale, and that's my image scale per pixel, excuse me, and my number of pixels wide and high. And these numbers taken together tell me how big my field of view is. If you're having trouble with your Platesolver, then come here and make sure that you've defined your scale and the number of pixels correctly, and remember to define them as 1 by 1. Other Platesolvers sometimes just ask you, or you configure it right then and there. Platesolve 2 takes the configuration details from the Sequence Generator Pro. Although I think you can go over there and configure it yourself, but it takes it from here. Now, to configure your catalogs and things, then catalogs are those, remember that Draper list I showed you several times now? You have to decide which one you're going to use. Actually, you don't have to decide. They both work pretty much the same from everything everybody tells me. And the way you do that is you go over and you pick a profile, and you, under Platesolve, which is also under the, right there on the Equipment Manager, you tell it to configure your catalog directories, and you just put them in wherever it belongs. As long as it knows where it is, it'll be okay. Now, This isn't a program about Sequence Generator Pro, but you don't need to download Platesolve 2. It's already there. But you do need to download a catalog for it. And again, as I said, either of these catalogs will probably work. You just have to remember to tell Sequence Generator Pro where the catalogs are.
So Alex, there are a couple of questions.
Yeah.
Joe asks how to calculate image scale if you're using a reducer or reducer and a flattener. And I think what he means is that if you're using a reducer that you're not exactly sure what your focal length is, so you can't calculate it. So how do you figure it out?
First off, you probably can calculate it because there's a number of things. My favorite is Ron Wadowski's CCD calculator. There's another one over at Star Arizona, and you tell them the name of your camera, the size of your and you tell them the name of your camera, the focal length of your scope, what the reduction factor is in your focal reducer and stuff like that. And it comes up with a number. And then me, because I'm particularly lazy, will go do a Platesolve. I'll take a picture and do a Platesolve. And the Platesolve will have as part of its information what the actual plate scale is. Or I'm sorry, the actual pixel scale too. That's one of the results of a plate scale or Platesolve. Okay.
So you do a blind solve.
I do a blind solve.
Data to put into your regular solve.
And that will tell you what the answers are. Now, I know I just said first you have to configure your telescope and camera. And then I said, and the way I configure my camera is to go do a Platesolve. Believe it or not, with the blind solve, that can sometimes get you through. If it doesn't, you can go to, like Star Arizona has a CCD calculator, I think it's called. And there's various other places you can get that information. Ron Wadowski's New Astronomy Press has it. Okay, did you ask?
And the second question, Linda asks, ask the exposure question a little exposure question a little bit differently. Instead of that, what is the optimum number of stars in the field? What is too little and what's too many?
I think 20 is good. 10's fine. I'll tell you what, that should do it.
In my experience, 8 is about the minimum. If you have less than 8 stars, it will fail.
I don't know if there is a number at that. I don't know if you can take a picture and have less than 10 stars. Can you?
It depends on the telescope. If the field of view is too small, yeah. There are instances where you can. And the downside of having too many stars is that your Platesolve will take too long. It's not that it will fail because there are too many stars. It'll just take forever.
Okay. Yeah. Okay.
Yeah. That's it for now.
Yeah. Okay. Okay.
Yeah, that's it for now.
Yeah. So remember what your catalogs are often, not in every case, because remember there are different plate solvers out there and they do them in different ways. But this is hint information. It needs it to know approximately which part of the catalog to look at. Okay. All right. And where are we? Starting location. Yeah, most of us are using a mount that hooks directly through our auxiliary port or through our RS-232 port directly to the computer. And so our ASCOM is communicating directly between the computer and the mount so that the computer always knows where the telescope thinks it's pointing. So our plate solvers can get that information directly. If you aren't doing that, then when you start a plate solve, there will probably be a screen that says, where do you think you are? Now, the reason that's necessary is because that tells it where to start looking. All right. Now, earlier we used the term, so you get your location from the mount. It's good if you maybe have done one sync on a star someplace. Remember we were talking earlier about going to a particular star and saying, I'm right here. And if you've done a 3-point alignment, that's fine. Most people have skipped doing 3-point alignments at this point because they don't matter anymore. Their go-to, they don't rely on their go-to as much as they used to. Now they're relying on plate solving. So if you're having trouble getting solve, it may be because your hint information on where you're starting is really off. And what you can do is go to a known star and make sure it is in the field of view and sync your mount through your hand paddle to sync to that particular star. Now, there's two kinds of solves out there, and Tolga asked about this a long time ago. Blind solve and regular solve, or a known position solve. With the known position solve, you think you know where you are. You're within a field of view or 2 or 3 or 4 of where you should be. Your go-to has gotten you pretty much where it's supposed to go. And your computer is communicating with your mount so that they know where each other are. You can also do a blind solve. The difference between blind and a known position is that with the blind solve, you don't have to know where you are. Unfortunately, it takes a lot longer to do a blind solve than to do a known position solve. Well, that may be true. Actually, blind solves are a lot quicker if you really have no idea where your known position is. You know what I mean? It's like if you don't know where to start, it takes a long time to do a known position solve, and it will probably fail. But if you know where you are in the beginning, it's faster to do a known position start. If you have no idea where you are, you can do a blind solve. A blind solve, the difference is, well, I'm going to get to the next slide and I'll tell you a little bit about this. Here are some names of things that are plate solvers. Okay. And I just went through and Googled plate solver and got a bunch of names. I'm going to say some things about them. Unimap, I'm not going to say much about because I know nothing about it. I know that it exists and it's out there and people use it, but I don't know anything about it. Pinpoint and LE. I've used Pinpoint and I've used LE. LE, the light edition or limited edition or something of Pinpoint, comes with Maxim DL. And it's a good product and it's very powerful, very well supported, kind of bulletproof, works pretty much all the time, just as it's supposed to, as long as it's got, you know, good picture to work with, not too much nebulosity, not too much noise and stuff like that. The difference between Pinpoint and LE is that the LE is a limited edition, so you can't use it in all the aspects that you might want to use it for. Many people think that they can use LE in other programs. Sequence Generator Pro, for instance, cannot use the LE edition. Sky Commander, I don't believe, can use the LE edition. Check on that before you make it a point, guys. I just remember in my buying these things through the years, when I found out that, oh, wait a minute, my edition of Pinpoint doesn't work yet, but Pinpoint's real good. It's a real good thing. And it's got other things in it besides plate solving itself, but we'll just have Elbrus. Elbrus is a dear respected elder and nobody pays much attention to it anymore. There's a line in the SGP manual that says that it's still here, but we don't support it. And Elbrus it does have a pretty good explanation of how plate solving works, at least for Elbrus, but it gives you an idea about it. Astra Tortilla is an interface that allows you to call other astrometry.net or ANSVR. These next two, they're the ones that were explained in that other package I showed you earlier. They explain how they got their system to work. They're both the same piece of software. The difference is that astrometry.net is on their computers far away, and ANSVR is basically on your computer. So you upload a picture to them, they analyze it and send it back to you in 5 seconds or 35 seconds or 45 seconds or whatever it is. and they tell you where you are. Both as ANSFER, which is Astronomy Net Server, there's a local edition of this. The software is on your computer, and you download a catalog that fits your telescope's field of view. And I don't know about you, but I just downloaded them all because I've got several telescopes, several cameras, and I just didn't want to do all that thinking. So I just downloaded them all. It takes a long time to download them into your computer, but they don't take up that much room, all things considered. But at any rate, they're the same piece of software. Their computers are faster than yours, and they've got their database right there where they can go through the whole thing. You've got your computer is slower, but you don't have to put up with download speeds. Astrometry.net, you need to be connected to the net, which you may or may not be able to do when you're on a distant dark mountaintop or out in the desert someplace. The Sky has a whole other system that they don't call plate solving, they call ImageLink. And ImageLink works the same way. The concepts behind it are the same. It finds patterns in the sky. Those patterns are coded, and it matches patterns that they've already looked through. And they've got a database of all the patterns. So they do the same thing the plate solving does, with a slightly different algorithm, just as the various programs do. PixInsight also has a system for finding stars and assigning them, so that you can do, I've never actually tried it, but I know it's in there. I want to be clear, though, that we understand the difference between the interface and the engine. Astrometry.net is an engine for, as I understand it, Unimap, AstroTortilla, and several others. These guys here are the interface. That is, you take the picture and you communicate on on AstroTortilla or Unimap, as I understand it, but then it sends it off to astrometry.net. Okay, if anybody knows different than that, again, please come to a presentation on plate solving on the Astroimaging channel. We could use the help. And that's all the stuff I prepared for today. So at this point, it's question and answer time. Where are we, Toga and Eric?
James was asking about Platesolve 2. Has anyone using it? Because he tried another software. It worked for a while, but now it doesn't. But he seems to think that he changed his equipment and he didn't update his profile. Okay. And that's something you need to do, right?
If you have changed equipment, you need to at least check your profile to make sure that it's accurate. I got to stop my screen sharing before I go goofy here. There we go. I don't know if that's any better, but it's me. Yeah, if you have changed your equipment, yeah, remember that hint information? That hint information is absolutely essential. Otherwise, it's just going to get lost. It doesn't know where to start. In order to help change your information back, do a blind solve, and the blind solve will probably come back with something eventually, and you can take it from there.
Did you see the question here? Which catalog would you guys recommend? PS2, APM, or UCA-C3?
Yeah, anybody got anything to say about that? Okay, go ahead.
Oh yeah, which catalog do we recommend? PS2, APM, or UCA-C3? As far as I think the UCA-C3 is the most popular one, as far as I know.
Yeah, I don't know that. I've asked this. I've seen this question asked many times, and I don't see an answer to it. You use whatever you feel is getting you the answers. You know, if someone's getting you the answers, keep with it.
John asks, are there any strategies for plate solving if you're in a star-poor area away from the galactic, I guess from the Milky Way? Well, again, it depends on your field of view, right? So if you have a very long focal length telescope with a small chip, it may be difficult. So you might have to do blind solving techniques. You might have to do 15, 20, 30-second exposures to have minimum number of stars necessary. But for a wide field telescope, I don't think it's an issue. For like a 500 to 1,000 millimeter refractor with a, let's say, a micro four thirds chip, like an 8300 or a 1600, you shouldn't have problems with number of stars.
Okay, I'm just starting to read the questions now, so. Okay, Glenn, where are we? Did I read someplace that when when your files are being sent up to astrometry.net that they go as JPEG files? Did anybody know that?
You can upload any kind that you want. It just the JPEGs are smaller.
Yeah.
But I don't think it makes any difference to astrometry.net.
Ryan, in SGP, the most popular plate solver is Platesolver 2, but there are 3 or 4 you can use. My setup starts with Platesolver 2, and then my backup is ANSVR. I never use astrometry.net because I just found it easier to put it on my computer, but I could go the other route. Yeah, Brian, we got the same answer.
Yeah, the SkyX image link is a very powerful plate solve. Like it will literally, if it's set up correctly, it will literally never fail. It's just the only problem with it. It only, it's a SkyX feature. You can't add it to SGP or, Maxim or anything else. It's built into SkyX.
Okay, Ray, did I solve them tonight? Alex solved my issues. I don't have any issues with plate solving. I doubt that. Not even a cloudy sky.
Ray left a little bit ago, but I think you helped him offline. That's
okay.
what I meant.
Sky, I tell them out to go to an object with a closed loop slew. Remember when I was talking about centering and the iterative, take the picture, move, take the picture, move, check. That's closed loop slewing. Okay. That's another word for it.
Yeah, that's a BISC word. Nobody else uses that. That's kind of pertains to SkyX, but it doesn't pertain to a power mount because you could use closed loop slew to any mount that's connected to SkyX.
Oh, Toga answered that question, I see. Yes. You don't, and if you go to Sequence Generator Pro or any place and tell your, you don't have to take a picture and plate solve it before you go to wherever you're supposed to go. You can tell the session management program that you want to take a picture of this nebula and it is at that location. Now go there. It doesn't need to take any pictures. It relies on your mount's go-to to go there. And your mount's go-to should put it within 2 or 3 or 4 or 5 fields of view. And if you can get it that close, then it takes its first picture and sees where it wound up and proceeds from there. That's so Morgan Dollar. Yeah, you're right on there. And John, is longer time better? The question is, are you getting 15, 20 stars there? If you are, you probably should be able to plate solve. If you aren't, you're going to need more time for exposure. But don't let them get saturated. Yeah, Morgan points out that you can get the camera rotation. And Ray's astrophotography suggests that you go with you do your alignment and you build your model first. Yeah, I'm not saying you don't need to build a model. Some people find their mounts like building models. Other people got their own ways of doing it, but the 3-step, 3-star alignment and stuff like that. That's useful. Oh my gosh, I'm only a third of the way through the questions. What is PEC? What does it have to do with plate solving? Nothing much. PEC is periodic correction, periodic error correction. And it doesn't work with plate solving. It just smooths out the motion in the right ascension, which really doesn't have much to do with plate solving.
Well, yeah, that's the reason why I didn't bring those up, because they weren't relevant to what you were talking.
We're just going through and make sure everybody, somebody bothered to make a comment. We want to make sure that it's, and I'm way behind the time because I was talking while you guys were talking.
Oh, I see. I just switched over to YouTube. I see some questions over there. And guys, we have a chat server in our website. It's what's our website? testing.theastroimagingchannel.com.
Yeah.
If you guys, we don't monitor the chat that's on YouTube. So if you guys have any questions, please go to the website, sign into the chat, and ask your questions there.
Yeah, I'm going to put that up on my screen here. Share my screen. And
so let me see what the questions are over there.
You see this area over here? These are the questions we're reading through. Is Pam Pro and SkyX are outside software? Pam Pro is a separate piece of software. I don't think it's part of SkyX, is it?
No, it's not. No,
I mean, I know it is. Does SkyX have an equivalent?
Yes, SkyX is a built-in periodic error correction.
Yeah, with T-point.
Part in it. No. It has nothing to do with T-point.
That's right. You're right.
It's so. But I find that Pam Pro is a periodic error correction software. That's all it does. I mean, that's the main. It does polar alignment and things like that. Yeah. But its main function is periodic error correction, and it works on pretty much every mount. It works. It'll work on astrophysics. It'll work for Paramount, any mount, pretty much. But because it's a dedicated periodic error software, it's just better than the one that's built into SkyX. So that's what I was telling the questioner over there. Yeah, like in SkyX, I'll give you an example. In SkyX, to measure periodic error, your camera has to be at a certain angle. The x-axis has to be either 360, or 180. But in Pam Pro, you can select which axis. You don't need to turn your camera a certain way. You could just take any which way and just tell Pam Pro, hey, this is my position angle, and Pam Pro will calculate the necessary corrections. So, and then I don't want to do this into a Pam Pro presentation, but actually that's a good one. We should do a presentation on Pam Pro.
Who? Somebody should. I've only used it.
I was able to, and here's another cool feature that Pam Pro has. You can measure your periodic error with Pam Pro, and then apply it to your mount, and then measure it again, and Pam Pro will calculate the leftover periodic error after the correction, and we'll make a compound curve. Not a new curve, but combining both curves to do like a refined curve, which will get your periodic error to like unreadable numbers, perfectly flat, unreadable numbers. So Actually, this is a good thing. We should do a presentation on Pam Pro.
We should, or have somebody who wrote Pam Pro. Oh, really? Okay. We'll work on that. Ray, I'm about halfway through the questions here, and you're asking about Pam Pro and PhD and stuff like that. No, I think Tolga's pretty well answered it. Pam Pro doesn't do that. It does other things. PhD has some stuff that acts like Pam Pro and I think calculates some errors. And they've got a predictive guiding routine that also works with your periodic error, but it's not the same thing. You need, there's a couple people asking about your image scale and plate scale. Your camera, you're going to need some information from your camera manufacturer as to the size of your chips. So, and the size of the pixels on the chip. Era, yeah, 250 will be fine. If the question is, does it work? If it's still pretty quick, guys, don't get hung up in like there's some ideal perfection. There isn't.
Yeah, there are not many questions you're going to ask in this whole hobby that you're going to get okay, black and white answer. It's always going to be yes, but, no, but. If if these were the cases, this will work better. If this is, it's always going to be, there's never going to be a black and white answer.
Okay. Yeah. I'm back about where I'm at 1908 in the time here. Guys, there are wiggle factors built into all the plate solvers. They go through and analyze the noise and get rid of things that, might be stars, but might be noise. They know how to do that. And they also don't need absolute precision in all these measurements. They have thresholds at which they count it as found, and then they check with other polygons or triangles or stuff like that to find out what it is. You know what I mean? It's like, so somebody said, oh, if it's a millimeter off, it's not going to work. No, that's not true. It'll still be kind of close. Okay. A straight flattener will not change the focal length of a telescope. Okay. Yeah. Okay. That's because there was some, there's some discussion earlier about how it changes the field of view, I think. And a straight flattener won't, but a reducer can. Yeah, you see what Astro Molly says here about proof would be to plate solve an image before the flattener and then after again. Guys, do some of these experiments yourself and go out on those moony nights, when the moon's out, you can't really get a good astro image anyway. And just do some of these things and learn, get a feel for how these things actually affect stuff. I don't ever want to be in a position where I'm giving advice to people to be sloppy. I never want to say, yeah, just go out and just do what you want. It'll be okay. No, there are some things you need to do to make really good pictures, but don't expect somebody else to be able to tell you exactly what they are for your rig and your set of patients and the temperature outside for you and everything else. There is no one solution to all of these things. So you're going to have to, some of these things, do it yourself. Okay, thanks. Yeah, somebody pointed out here that, in addition to what we're talking about here, there's There's other work to be done with plate solvers. We're talking about an astroimaging is just make sure that your picture is framed correctly. What about plate solving from an old image when you don't know the field of view? First off, if it's a fits, if it's a fits image, you may know it. You may not know it, but you can read the fits header and it may be there. Secondly, a blind solve should take care of the problem. The only place where I have troubles with blind solves doing that is when you have a lot of nebulosity, because nebulosity can confuse things. Devin Boggs asked, what plate solver would you recommend with use with ASCOM? I like Platesolve 2. I like Pinpoint. The nice thing about Pinpoint compared to, another nice thing about Platesolver 2 compared to Pinpoint is that $150 you don't have to spend. Pinpoint's for, or Platesolve 2 is free, but astrometry.net is also free and stuff like that. So Devin, as far as use with ASCOM, I don't think that's an issue. You have, remember I talked about the interfaces. I think most of these interfaces will interface with an ASCOM mount, as long as you just start your ASCOM mount, it should do. We're not use a planetarium program with plate solving. No, it's not at all redundant to use a planetarium program with plate solving. Planetarium program can tell you what your coordinates should be. I want to go image M42. Well, go check out M42 and it'll tell you what your coordinates should be. Great, go for it. And so that's what you need to do. Your planetarium program may also have controls to control your scope and stuff like that. So yeah, go ahead and do that. Ray Graylick software. That's what I thought, but I didn't want to say it. Okay. I mean, use the blind solver just when Platesolve 2 is not working. Chow, where you say the blind solve in SGP when Platesolve 2, yeah, you get to choose your primary and configure that in your equipment profile under Platesolve. But then you also choose a backup, and your backup can be either astrometry.net or ANS server or anything else you want, I suppose, too. But I think the standard thing that most people will have is Platesolve 2 as their primary, and ANSFER or astrometry.net. And that really depends on whether you've got an easy internet connection or not. Yeah, as Glenn has pointed out, that a plate solve can tell you exactly where your telescope is pointed, and that can usually be transferred back to your planetarium program. Nicole, try ANS server. What is the recommended plate solving tool for local plate solving? ANSVR. That's one of the things we talked about today. You just don't know enough about it yet. My primary, yeah. Joe has got it just right. Platesolve 2 is my primary. Okay, I think I've been through all the questions now. Guys, get your last questions in if you're going to ask anything, because we'll be wrapping it up. We've spent an hour with you tonight. And next week we'll be back. We're going to do a session similar to this using, except we're going to be talking about the polar alignment tools that one can find in PhD. Now, the reason we're going to use the ones in PhD is because those are the ones I know about, and you're relying on me. And that's really sad, guys, because I know that there are other people out there that know how to do this stuff and can do these kinds of presentations. They're not really all that hard to do. What you're basically doing is putting a few pictures together and then talking about them as you go. And we need people to help us do that. Otherwise, you're going to be listening to me and Tolga and Eric and us all the time. And I think you all should be able to contribute a little bit to that now and then. Please get a hold of us at the Astro Imaging channel. There's contacts on the webpage where you can contact us. Next week, we're going to be talking about PhD's polar aligning tools and a little bit about polar aligning, the same way we talked about plate solving tonight. The week after that, Molly Wakeling is going to be telling us about PixInsight for beginners. And on March 3rd, Makila Weller is going to be talking to us about something near and dear to all our hearts, specifically how to get this done on a budget, if you know what I mean. We spend an awful lot of money on this kind of stuff, and you don't need to. You can take wonderful pictures you can show everybody in your family and have, just be really proud of, and everything else. Don't show them, certain places, because they'll pick them apart. Mean, nasty people. But we're going to have a presentation about doing it on the cheap. So that'll be cool. Ciao, I have an interesting one. By interesting one, do you mean you have a question about something? Let's see. Okay, so here we got a picture. Can we blow that picture up? Is my screen sharing?
Not yet.
Am I screen sharing now?
Now you are.
Okay. Okay. What is the problem with this? Let's see what Chow's typing in. Where are we? I've got too many programs I've got to work with. Nope, I don't want to do that. It's an unknown light spot in my image. Yeah, Joe, I can't get anything. I mean, I'm looking at what you're talking about, and I'm not seeing what if you're talking about this mist shape in the star, is this the same field? Yeah, this is the same field. And then in one, you've got this big bright star. You sure? I don't know what that is. Anybody else have any idea? Type it into your chat room over there.
Aeroplane.
That could be, but it's awfully specular, meaning.
Yeah, if you have a strobe that goes off on an airplane just in the field of view, I've seen those pop up.
Yeah, but you usually have more than one light on an airplane.
Yep, but I've seen this.
Has your neighborhood lately been visited by little green men or anything? Okay, maybe not. Yeah, it's aliens. It's aliens. Well, if it were a satellite, yeah, it'd have to be a very short exposure not to show motion. But as if it were coming right at you, that is exactly what they look like from what I've heard. I don't really know what I'm talking about there because I've never had one come right at me. What is that? Okay, we're not going there. Okay, stop sharing. I don't even know which program I'm in anymore. Okay. I asked a couple of people lately about making presentations, and I get this reaction. Like one guy said, "Oh no, you know, I don't know how to do that kind of stuff." And another guy said, "Oh, you know what? I'm not all that." What did he say? "I'm not that hotshot an imager." If any of you guys have seen my images, you know that I'm not really not all that hotshot an imager either. You know, that's not the point. The point is that we're all in here kind of discussing things. This isn't the advanced imaging conference or anything like that. This is a bunch of people. I mean, I am sure that some of you guys learned some stuff about about uh, plate solving today, you know, and um, uh, please join us. We need people to come and talk on the show, get in touch with us, and volunteer to do something. Find something that you really like, that you think you know you've learned how to do, and you're willing to tell somebody about it. Don't worry about the fact that we've already done it at one point or another in our shows. If you think it's worthwhile and people would like to know about it, you know, let people know about it. Okay. Okay, that brings us to an end for the night. So thank you, everybody. And we'll see you next week when we're going to be talking about polar alignment. And Molly is going to be talking the week. Yep. Why am I talking? Okay, goodbye.